Hello and welcome to Chatterjee Tutoring. Today I'll be going over this LeetCode problem number 269, Alien Dictionary. Let's first go over the problem statement. So it says there's a new alien language that uses the English alphabet. However, the order among the letters is unknown. This means like in English, the ordering of the letters is A, B, C, D, E. But in this new alien language, it could be E, C, B, D, A. It could be. So we are given a list of words from the Alien Languages Dictionary, and we are given that the words are sorted lexicographically. What does lexicographically mean? It means that if there's a string S and T, S is lexicographically smaller than T if the first letter that is different between the two strings is smaller in S than in T, or the length of S itself is smaller than T if all of the rest of the characters are the same. Given these words, and given that they are lexicographically sorted already, we have to return the minimum alphabet that is possible, that is conforming with these words. Let's go through the first example test case. So we are given these words, and we have to find out the alphabet that matches these words. So in this case, the actual answer would be WERTF, because this is the minimum alphabet that corresponds with these words. Because, for example, we can see that the W comes before the E, so that's why W is before E in the alphabet. Over here, we see that the first two words are almost the same, except this T and this F are different. So we can see that T comes before F in the alphabet. Then we can see that E comes before R. We can also see that R comes before T because of these two words. And that's all the relationship that we need to know in order to find this ordering. So how would we do this? So first of all, we need to go through each word and find out the relationship between the two adjacent words. So for example, let's go through here. So for the first two words, the T and F are different. So let's denote that as T with an arrow to F. This means that T has to come before F in any alphabet that we make. Next we have W comes before E. Then we have R comes before T. So we'll just denote it over here. Next we have E comes before R. And that's all the relationships that we have so far. So from these relationships, what can you notice? Well, actually, we can combine some relationships together. For example, the first one and the third one, we can combine to make this, because we know that R comes before T and T comes before F. So by association, we can say that R also comes before F. Similarly, we can say that for the second and fourth relationships, we can say that W comes before E, E comes before R, and we can also combine these two to make W, E, R, T, F. And if you notice, this is exactly the alphabet that is the answer. So what did we get from this? Basically, our approach could be just from each adjacent word, we can make some relationship in a graph, and we can get some relationship between each adjacent word, and we can store these relationships in a directed graph where there's an edge between letters U and V if U has to come before V in the alphabet, or U is lexicographically before V in the alphabet. This way, once we have all the relations in place and we have fully constructed the graph, we can then perform a topological sort on the graph in order to get the alphabet back and return it from the function. Let's go through another slightly longer example. Here we have a bunch of words, a bunch of two-letter words, and let's go through building the graph and then topologically sorting it. First, we see that since the first two letters are the same, we can see that E comes before X, first of all. Then E comes before Z. Then y comes before a, so we can put that over here. Then we have a comes before x, so we have another arrow going like this. We have z comes before y, so we have an arrow between these two. X comes before m, so we have another letter m. We have y comes before a, so this already exists, this relationship, so we don't need to make another edge between those two. We can just use the previous one that we already have. And y comes before m, so there will be an arrow like this. So now we have our graph. It may look messy, but this is what we have so far. So now the next step is to get an ordering that satisfies all of these conditions. So to do this, we perform a topological sort. So what is topological sort? Topological sort is a function that takes a directed acyclic graph, or DAG for short, and it makes an ordering between all of the edges so that if there's an edge between nodes u and v, it guarantees that in the ordering, u will always come before v. So this is exactly what we need in this problem, because we have a bunch of relationships between letters, which are represented as nodes in a graph. And we need an ordering such that if there is some relationship between two letters, where one letter must come before the other, then we can put that into the ordering and get out the result like that. So how does topological sort work? There are two main methods of doing it. The first one is called Kahn's algorithm, or it's a breadth first search. And the second one is the depth first search approach. Okay, so let's first go over the breadth first search approach. So in order to do this, first we figure out the indegrees of every single node in the graph. So an indegree means basically the number of edges that are going into a node in the graph. So for example, in this one, we have 0 edges are coming into E. So we have 0 here. 2 edges are coming into X, 1 and 2. 1 is coming into Z. 1 is coming into Y. 1 is coming into A. And 2 are coming into M. So these are our indegrees. Next, we keep a queue of all the letters that we want to process. And initially, the queue will start with all of the letters that have an indegree of 0. That means there's no edges that are going into these nodes. So these nodes can be first in the ordering, and that will not harm anything because there's nothing that can come before it. So in this case, there's only E. So we'll put that into the queue. And then while the queue still has letters left, while there's still letters that we need to process, we can pop from the queue. So we get E and this comes out. And we push E to the result. So if we have a result over here, we can push E to the result. And then we can say that for every node that E is connecting to that has an indegree of 1, that means E is the only node that comes before that one. We can add those nodes to the queue. So for example, here, E comes before Z. So in this case, if we remove E from the graph because we have already processed it, we see that these edges go away, E goes away, and we are left with X having indegree of 1 and Z having indegree of 0. Because Z now has nothing that has to come before it. So now, what we can do is we can push Z to the queue because Z has an indegree of 0. Now we pop from the queue. We are currently processing Z, and we can push Z to the result. Next, we remove Z from the graph because we're done processing it. So since we remove Z, this edge also goes away. And now y has an in degree of 0 because now there are no nodes going to y. And we're also done with z. So now since y has in degree of 0, we can push y here. We process it by adding it to the result, popping it from the queue, and deleting y from the graph. So here, we delete this edge and this edge between y and its adjacent letters. So after this happens, a now has an in degree of 0. We can push it to the queue, and we see that if we pop a and push it to the result, remove it from the graph, then x now has an in degree of 0. So now we can have x in the queue, and now we process x by popping it, pushing it to the result, and deleting this from the graph. And now m is the only one with 0 left, so we can just push that to the result, close that since we have no more edges left, and we are done. So this is now the resulting string that we can get from that ordering. So that was the breadth first search approach, also called Kahn's algorithm. So now let's take a look at the depth first search approach to this problem. So for the depth first search approach, we want to go through all of the nodes and depth first search on each node. And while we are depth first searching, the last node that we come to, we will push it to the front of the result. So let's look through this example one more time. So let's say we start at any random node. Let's say we start at A. From A, we want to do a depth first search. So this means we first go through all of the adjacent to A, and then at the end, we can come back to A and push it to the result. So in order to do this, let's first go to X. So from X, then we go to M. So M does not have any neighbors, so we can push it to the result, but except it will be at the back because M is the last one in our ordering. And then once we are done with M, we can circle it in red, which means that we have already processed M. So now we go back to X. So X does not have any more neighbors, so we can also circle it in red, meaning we are done processing that one. We come back to A. We are done processing that one. While we are going, we keep pushing it to the result. So now we are done with these 3 nodes. So now we go through the next set of random nodes that we come across. Let's say the next node that we go to is Y. So now from Y, we see that both of the adjacent ones that from Y have already been visited and processed. So now we can just push Y to the result and circle it in red, meaning we are done processing that. Next, let's say we go to E. Then from E, we see that X has already been processed, but we can go to Z. Z has not been processed. We process it since it has no more neighbors that have not been processed. We push it to the result, and now we go back to E. We process that one, push it to the result, and we are done because all of the nodes have been circled in red, meaning all of the nodes have been processed. So that was the DEFS, or depth first search approach. So if you notice, both of these approaches got the exact same answer, and that's because for this specific problem, there is only one correct answer that is possible. However, if we add another node, let's say a J over here, and also make it connect to Y, then from E, we cannot go to X because there's another one going to X. But from E, we can go to either J or to Z first. And then after that, we can go to Y. So both of these are valid orderings. I mean, like, if we have E, Z, J, and then the rest of that down here, or we have E, J, Z, and the rest of that over here, both of these are correct orderings and are possible solutions. So now that I've gone over basically how the program works, let's go over the implementation in code. In this case, I will be using C++ to show it. First of all, we need to keep track of all of the data structures that we'll be using in order to represent the graph and ultimately come up with the solution. First of all, this vector of unordered set of character called ADJ for adjacent is the adjacency list representation of a graph. This is size 26 for 26 characters in the English alphabet, lowercase, and it means that for each of the 26 characters, all of the characters in the set at that position are the ones that must come directly after that character because of a relationship that we found from the input. Meaning that that character in the set has a directed relationship to the character that we are indexing. Next, we keep a vector of int called in, which represents the in degrees, which is also size 26 for each of the 26 characters. So next we come to this loop. So we loop over every word except for the last word because we want to process each adjacent pair of words to get the direct relationship between the characters. Then for each of the characters in those two adjacent words, we first check if they are not equal. If they are equal, then we cannot make a relationship between them two. In this first example, if we make a relationship between W and W, it doesn't mean anything. We have to go to T and F in order to make the relationship. So once we go all the way down and we make sure that we have not already encountered this relationship before, this is what this if statement means, then we increase the in degrees for that character, and then we add it to the adjacency list for the first character. And then if we find such a pair of characters, then we break. So this pair of adjacent words is already processed. And this if statement is basically saying if there is a word and then there is a word after it which has less number of characters but the exact same characters in the rest of the string, then this is an impossible lexicographical order and therefore we have to return an empty string. For example, if we had an input of ABC and AB, then this would be an impossible lexicographical ordering because even though all the letters are the same, the first word is longer than the second word, which is not allowed. If all of the characters are the same, it must be that the longer word is after the shorter word in the lexicographical ordering. Then we need to create the queue that we will use for the breadth first search. In order to do this, first of all, we need to know which characters we have seen in the input, meaning which characters exist in the input space. So this basically loops over every word and then every character in the word, and then sets that character that we have seen it. Then we construct the queue, and then for each character, if we have seen the character and the in degree of that character is 0, that means that this is a possible character to start off our queue with because there are no characters that must come before this one. Then we push it to the queue. The next step is we have to go through all the characters in the queue and then process them one at a time. So we keep our resulting string, and while the queue is not empty, we get the front and we pop it and we push it to the result. So these three statements are standard. And then the next part, for the I in the adjacent of that character C, that means for every character that is directly after this current character that we are processing, we must remove 1 from the in degree of that character, because we have just processed the current character. So we essentially remove the current character from the graph. So this means that there's one less edge going into the next character. So we remove 1 from that in degree. And then if the next character's in degree is 0, then we push it to the queue. If the in degree is 0, this means that this is a possible next character that we can process, because there are no more characters that must come before it. At the end, we check again if any of the in degrees of any of the characters is greater than 0, meaning that there are still edges that we have not processed. Then this means that there's a cycle in the graph, or something is not correct. So we return the empty string. So this basically is a cycle checker, which means that, for example, the input is A, B, A. This is not possible because A comes both before and after B. Then it's an impossible lexicographical ordering again, and we have to return the empty string. So this checks for that. And in the end, we just return the resulting string. Next, let's move on to the depth first search approach to this problem. So the first part of the problem is exactly the same. All of this. We first create the adjacency list, the scene array. We create the graph. We create the adjacency list from the input array. And then we check for each character in all of the words and check if they're seen. But here's where it starts to differ. First of all, we must keep a list of characters as the resulting instead of a string, because a string in C++ is just like a vector or an array list in Java, meaning that its underlying data structure is a raw array, meaning that if we wanted to push to the front, this would be a very, very inefficient data structure to use, especially since we are pushing every single character that we see to the front instead of the back. So that's why we must use a list, which in C++ is a linked list representation, meaning that pushing to the front takes O of 1 time, instead of the O of n time that a vector push front would take. Then we keep an array of 26 size, which is the state. So there are 3 possible states that any character can be in. The first one is 0, which is just unvisited, and which is the default for all of the characters. So that's why I initialize it with 0 here. The next possible state is 1, which means that we are currently in the process of finding out all of its children and pushing all of its children to the topological sorted array. And we have not processed this node yet, but we have visited it. And then state 2 means that we have already visited and completed this node, and we are just done with this character. So those are the 3 states that are possible for this state array for each and every character. Then we loop over the characters and we say that if we have seen this character and not topological sort of the result, the states, this current character and the adjacency list, then we return empty string. So what does this mean? So first, let's see the top sort method. So for this top sort method, we take in the result, which is a list of characters that we have below, the state, which is also an array of size 26 that we also have below, the character I, which is the current character that we are supposed to be processing, and the adjacency list representation of the graph. So first of all, we check if the current character has already been visited. So here's where the states come in. If the state is 1, that means that we are currently processing this node, but it has not been fully processed yet. that means we have visited it, but then we went into its children. If we reach a node that has a state of 1, this means that we have cycled around in the graph. So this means that we have a cycle and we immediately return false. So in this case, returning false means that we have a cycle and this input is impossible to be a lexicographically sorted alphabet. The next that we check is if the state is 2, that means that we have already processed and finished processing this node or this character. That means that this is a different call to topological sort altogether. So we just return true. That means there's no cycle, but we just do not want to process this node. The next thing that we do is we set the state to 1. This means that we have visited the node, but we have not processed it yet, because the next thing we do is we loop through all of the adjacent characters to this character. So what we want to do is we want to first loop through all of the children to make sure that all of the children first get processed and get pushed to the result. And then after all of the children have been processed and the top sort function has been called on all of the children, then we push the current character to the front of the result. We set the state to 2. That means we are done processing the current node and we do not want to process this current node anymore ever again. And then we return true. This means that there has not been any cycle and the topological sort was successful. So if you notice here, the only possible place that we can return false is either if we loop back on a node that has a state of 1, or one of the children has a cycle. So if one of the children has a cycle, which is shown by this not operator over here on the topological sort on the children, then we return false also. So after this topological sort has been called on all of the characters, then we construct the resulting string. We push back all of the characters in the resulting list that we calculated above into the resulting string, and we return the string. And that's it for this video. If you have any questions or comments, please leave it in the comment section below so that I may improve my future videos. And if you have any suggestions on how to improve the videos, please also leave it down in the comment section below. Other than that, have a great day.